Swayam Prabha. Digital India. Educated India.
Hello students, welcome to our next lecture on topic of introduction to probability. In our last lecture, we learned that whenever we have to take any decision, we have to essentially deal with uncertainty, and uncertainty can present itself in form of aleatoric uncertainty, which sometimes we call as irreducible uncertainty because it's characteristic of any data or sample that we record, or epistemic uncertainty that stems from limited or lack of knowledge about the system under consideration. As our models improve, the epistemic uncertainty can be reduced. However, aleatoric uncertainty has to be characterized, quantified using various concepts of probability. Hence, whenever we talk about signs of risk, decision making, and resilience, probability becomes indispensable mathematical tool, and hence we will cover various aspects of probability in this lecture and following lectures. So in the outline of this particular lecture would be, first of all, we'll try to understand role of probability in engineering. I'll try to motivate the case with help of an example, that how a typical real world problem can be solved using various concepts of probability. In that particular example, you may notice a lot of terminologies or technical words coming. So, no need to worry at this particular stage, even if you are not familiar with few terminologies. As we will progress ahead in this particular lecture, we will talk about that. But idea of that example is to introduce you to how problems can be designed in world of engineering and how concepts of probability would come in handy when we have to solve these particular problems. After that, we will look into some fundamental aspects of probability, some definitions, some mathematical forms that are often encountered whenever we are going to deal with concepts of risk analysis and decision making. And then we will conclude our discussions with sample space and events in this particular lecture. When we talk about decision making uncertainty, let us take more of an engineer centric view that what we are essentially looking for. So we understand that we have to design engineered structures or infrastructure systems for worst conditions. Now, what these worst conditions are, how we quantify that what is going to be worst scenario. If we take one of the possibilities that has been historically extreme and we design for that, it may happen that that particular event was just an outlier. It may not happen again in life of an infrastructure. Hence, we may end up with overinvestment. On the other hand, it may happen that the recorded data that we are using to make decision is of such a short duration, let us say 10 years, 20 years, that it would not even cover the design and planning horizon of our infrastructure system. And in that particular case, we are going to make a wrong decision on the underinvestment side. And this is precisely, we are always in dilemma that what level of extreme our infrastructure system should be designed for. I will be using lot of examples from floods because that would be our center point whenever we will talk about examples of decision making. And one example in the flood would be that should we consider that the entire area around river would be submerged if flooding event happens, and hence we adapt for that, but that is going to be a very costly exercise. Then, as I already mentioned, that there are going to be aleatoric versus epistemic uncertainty that we are always going to deal with. Whenever we are going to deal with complex infrastructure systems having multiple components interacting with each other, it would be next to impossible to fully characterize the system. That is, epistemic uncertainty would always be present, does not matter what kind of model, what kind of system modeling approach we are going to use. And when it comes to aleatoric uncertainty, we will try to characterize it in best possible manner, as it would be evident from a few examples today. There would always be trade-offs between costs and benefits, because our hazard or event against which we are designing our infrastructure system is having uncertainty. Hence, the costs associated with mitigation of particular hazard or adaptation to particular hazard will also have that uncertainty inherited from the unknown elements in the risk itself. And then when it comes to benefit, because we are essentially planning to cancel out that particular extreme event, so the benefits would also be probabilistic. Hence, there would always be trade-off between costs and benefits, and that too would be contained with certain elements of uncertainty. And finally, we have, once our infrastructure design is planned, built, finalized, we have to also answer this particular question, that what is the reliability of our system? How safe is safe enough? Can we say that this particular infrastructure is 100% safe throughout its lifetime? Which is a big ask, because we don't know the full spectrum of hazard itself. Hence, ensuring 100% reliability for any real world infrastructure system to hazards like floods, earthquakes is a big ask. Hence, it becomes very important for engineers to quantify and communicate these uncertainties in form of probabilities or reliability measures effectively, to instill confidence in the users, policymakers, and stakeholders. Now, we have discussed so many things philosophically, that what is role of uncertainty A versus uncertainty B, but let's try to understand this with help of an example. Let us say that we are considering installation of a coffer dam. In next slide, I will show you a photograph that how a typical coffer dam looks like. But let us say that there is a river, and here we have to build some bridge. So if bridge has to be built here, some foundation works need to be done. And when these foundation works need to be done, we have to essentially divert the river around this particular construction site. So this is our foundation site, and to divert this particular water around this construction site, sometimes we install a temporary barrier, what we call as coffer dam, so that river water does not enter into the construction site. Now, one question that we face here is that what should be height of this particular coffer dam? We can measure average level of water in river. Let us say it is 5 feet, and we design for that. Or we take what was the maximum water level in last monsoon. Let us say it was 6 feet, and design for that. And there can be n number of decision points that we can take. However, what is the confidence around choice of 6 feet or 5.5 feet or 5 feet? That is where this probability would come into picture. What we do, we collect really long as possible time series of flood levels, both in terms of how many events happened and what was the depth of water above average water level in each of these particular events. And we try to calculate their central tendencies or dispersion around central tendencies. Central tendency could be mean, it could be median, it could be mode, and dispersion, a typical measure of dispersion is variability or variance around that particular mean. And based on that, we try to come up with something called as estimates. So from data, we get into estimates. And now if you relate it to our previous discussion on aleatoric uncertainty, this is one typical way to characterize aleatoric uncertainty. Given data, how we can characterize the probability of any event exceeding for what I have designed a particular infrastructure system. Now, if we go back to our question, it says that suppose that occurrence of flood follows Poisson distribution. Right now, you may ignore this particular term if you are not familiar with that. We will have detailed discussion, but it is one of the probability functions that is widely used in real world. But it basically tells us that there is some variable that follows a probability distribution, and the mean occurrence rate of flood is 1.5 times per year. So in 1 year, expect 1.5, in 2 years, expect 3, and so on, number of floods in that particular setting. And the elevation of each flood is exponentially distributed with a mean of 5 feet above normal water level. So there is another information. Now you see that when we talk about number of floods, these events are going to be discrete. That is, we can count 1, 2, 3, 4, and so on. When we talk about level of water in the river, it can be 1 meter, it can be 1.1 meter, it can be 1.2, it can be 1.25. So it will take the values which are more or less continuous. So we have already introduced ourselves to two different kind of variables that we encounter in decision making. One are continuous and one are discrete. And as the name suggests, what you can count is discrete. What can take any value between minus infinity to infinity is going to be continuous. Now, this is information about the hazard, which is flood in this case. What is the consequence of hazard? Whenever flood levels are exceeded, water is going to enter into construction site. There may be machines, there may be workers, and as a result of which there may be submergence and heavy loss of life and property. Assuming that there is enough warning time available to evacuate people working in that particular site area, equipments, machines are still at higher risk. And you can imagine, if bridge is being constructed, there would be cranes, there are going to be heavy equipments like rollers, etc. There may be a machine doing pile foundation. So all these equipments would cost in crores or millions of dollars. Hence, this is going to be a big loss if they are exposed to particular hazard. So here we have another information that each time this coffer dam is overtopped, that is when water enters into the construction site, the expected loss would be of order of $25,000. I have just used some notation to not have multiple zeros, but it can scale, this discussion can be scaled to any currency value of interest. And here the question is, determine the optimal height of the dam. And some other data is given that construction cost of coffer dam is given by CE is equal to C naught plus 3000 H. That means as height of coffer dam increases, cost would increase by multiple of 3000 with each unit of height. And let's say that here we are talking about per feet of height, we have to spend another $3,000 or whatever currency we are dealing with. And C naught is a fixed cost. Does not matter you built 1 feet of coffer dam or 2 feet or 3 feet, you still have to build foundations, and that is going to be a fixed cost. And question is, what should be the value of H in this particular case? As I said, that if you look into the photograph of coffer dam, this is a typical photograph where you have a river and some construction work is going on, and in center you can notice certain machines being placed, and outside area is completely wet where river is in full swing. Some diversion has happened around that, and this particular area is fully dry. So now if water is able to overtop this top of coffer dam, it is going to enter and result in submergence. And this coffer dam is used at multiple locations, multiple places across the globe to do construction where water table or water level is particularly very high. So how we would solve this particular example? Again, as I said, let's not worry about the mathematics right now. I'll just do this particular example end to end, and it will tell us which concepts are necessary to solve problems like this. And this is one of the simpler engineering problems where a lot of data is known or given or assumed. But in real life, we would just be given a problem and we have to use best of the mathematical tools available to come up with the solution. However, this is not a bad example to get started with. So let us look into what are the unknowns. So where what is unknown here? We do not know how many floods. We have some probability that on an average 1.5 floods happen per year. But again, it's some central tendency. So this can be that in 1 year we may have zero floods, or one flood, or two flood, or we may also have infinite floods. But as you can intuitively sense that probability of having 1.5 floods per year is going to be the highest because that's what has been given. And as we go towards 10, 20, 30 or infinite floods, probability of getting infinite floods is going to be close to zero. And this is exactly what these probability distribution functions tell us, that how fast these distributions are going to decay towards their tails. What is the probability of having any value far away from the mean, or at the mean, or on the left side of the mean? But these are essentially these functions that contain this information about probability of x greater than equal to x or less than equal to x, and so on. We will talk about this x less than equal to x when we talk uh, about random variables, that how we can use same variable in a same formula two times without making a distinction. But again, I'm just setting a stage for maths that is to follow from here. So this is what these PDFs or CDFs will tell us. But one thing is for sure, that these floods are going to be discrete events. Number of floods are discrete events, and hence it is also given that we are going to use some distribution name called as Poisson distribution, which is specifically used to model discrete events. That is one thing. Second thing that we don't know here is that if flood happens, what is going to be depth of that particular flood? Would it be 1 feet? Would it be 1.5 feet? Would it be 1.75 feet? Or would it be 5 feet above the average level? Or it would be infinite feet above the average level of river? Now again, as you can imagine, it is given that central tendency of flood is around 5 feet as given in the question. As we go towards infinity, infinite flood probability would be close to zero. I cannot necessarily say it would be zero, because it can be a really really high flood, 1 in 1,000 year event. Again, we will talk about these extreme events into our discussions around EVD. But theoretically speaking, I cannot rule out any of these extreme events when I am talking in probabilistic sense. Hence it is important to understand entire spectrum of events that our infrastructure can face. But more importantly, this particular variable, that is depth of flood, is essentially a continuous variable, and continuous variables are typically characterized or quantified, their probabilities are quantified using different families of distribution, out of which exponential distribution is one of the important distribution that we will discuss in more detail. Now when we talk about damages, first thing we have to look into expected damage because of each flood. So it is specified that whenever each flood event happens, we are going to lose $25,000 because of inundation. And this particular flood would ultimately cause damage if height of water is greater than h, because if we have to provide a coffer dam of height h and that particular h is overtopped, only then water is going to enter into our construction site. So the range under consideration where flooding can happen inside my construction site would vary from h to infinity, not from 0 to infinity or from minus infinity to infinity, because anything greater than h is the flood event for me, because for that h I have provided the protection, or I have already provided measures to adapt to that particular flood. Now it is given that it follows certain family of distribution px dx, and I also know that it is following a distribution called as the exponential distribution. As I know that it is coming from a family of distribution, I can replace this px by its exact analytical form, which takes forms lambda e raised to power minus lambda x dx, and integration limits remain the same. That is, we will integrate it from h to infinity. Now, interestingly, if we for a while we forget what this exponential or Poisson is, we have gone from an abstract form to an exact mathematical expression that can now be solved either analytically or computationally or approximately. And that is the power of probability in the context of quantification of risk. Because initially we were just talking, okay, flood may happen, may cause damage, but now we have written a mathematical function that can be solved and give us the value or an expected value of damage from each flood. Here I have solved it for you, but we will revisit this example multiple times in our discussion, and we say that for each of the damages, for each flood, the damage comes out to be 25,000 e to the power minus h by 5. That means as height increases, that means probability of that particular flood also diminishes, and this exponentially decaying function takes care of that. Now, if you see, if I put h equal to 0, e raised to power 0 is going to unity, and hence the expected damage is $25,000. That means even if my height is slightly exceeded the height of coffer dam, I am going to have some amount of damage. Now, here we have not accounted for number of flood events at all. So what we will do, we will try to assimilate this particular discussion into that what if we are going to have multiple flood events in a given year. So for all floods, the total loss that we are going to encounter is 25,000 e to the power minus h by 5 multiply by I, where I are the number of floods, but we don't know I. Again, this may be, I can take value of 0, 1, 2, 3, 4, and so on. And again, we know that what is the probability distribution function around I, because we already specified that it follows a Poisson distribution, and I can be from 0, there may be 0 floods, all the way to infinity flood. As soon as we specified that this also comes from a family of distribution, we can also write its mathematical form and convert our this abstract expression into something which has a exact mathematical form. So goes from sum from I to infinity CF, and it may look very intimidating at this stage. We can still solve it fully and get our answer as 75,000 e to the power minus h by 5. Now, if we talk about total costs, our total costs are going to be the fixed costs plus 3,000 h plus 75,000 e to the power minus h by 5. That is the cost for having an insufficient height coffer dam. Now, let us focus on this particular expression, that what happens when we decide to build no coffer dam, or we just flush the coffer dam top with the average water level in the river. Our H will take value of 0, as a result of which we are not going to spend any money on construction of additional height coffer dam. So our total costs come out to be C naught plus 75,000 e to the power minus 0 by 5. So C naught plus 75,000. Now, this is what we call as indirect costs or unrealized costs, taking over what we expect from the direct costs or the construction costs. When we look at an expression, it may, if we just focus on the cost expression is simply C naught plus 3000 H. Our intuition will say, let us minimize H so that our direct costs are saved. However, when the indirect costs comes into the picture, that is 75,000 e to the power minus h by 5, that immediately tells us that indirect costs at h equal to 0 supersede all the costs that are fixed costs, as well as the cost per unit of height, because of the losses that we are going to incur because of exposure of the assets that are in place. Now, this example, although it has a lot of mathematics, it teaches us very important lessons. That is, if we can fully characterize the aleatoric uncertainty, we can really translate it to decision making. We can really translate our abstract understanding of a system into quantifiable measure. Now, once we have this particular function, we have to determine the optimal value. From the theory of optimality, we know that if we differentiate this particular expression with respect to height and equate to 0, we get our answer. But again, that is not the point for this particular problem. But here we will end up with a finite value of height, which comes out to be 8.05 feet. That is, if you provide 8 feet high coffer dam above the river level, your losses are going to be minimal. Reaching to this number intuitively is almost impossible. And that is what probability would do for us. That is, convert our intuition into a mathematical vacuum. Let us consider another simple example where a new wastewater treatment process is proposed. And because this proposed waste treatment process is based on new concept, it's a new innovation that has happened. Don't have enough monitoring data. Its efficiency is unknown to us at this stage. Project engineer has two choices, that let's build a smaller unit or let's build a larger unit. So A is going to be smaller and B is going to be larger. As you can imagine, if you have to build a smaller unit with same technology, costs would be lower. If you have to build larger unit with same efficiency, the costs are going to be higher. So we have to make a decision. We cannot just go say that, okay, let's build both A and B and let's see which performs better. But that's not how engineering works. We have to make a choice, A or B. But here the problem is we don't know the efficiencies. If efficiencies of the process is high, that means A would suffice, because even in smaller area, it can do large scale purification. However, if efficiency of this particular technology is actually low and we go for lower size or lower dimension treatment plant, we may have spillages, we may have environmental violations, we may not have wastewater treatment done to required efficiency, and hence indirect costs may take over the savings that we have made from investing into a smaller plant. Hence, B cannot be ruled out. What if actually that the technology is not as good as we initially thought, and we have to now choose that which one we should go for. In this case, we would need certain additional data. That is, we will try to capture this in form of some decision tree. That is, should we go for A or should we go for B? If we go for A, we have two possibilities, that we may have high efficiency or we may actually have low efficiency, which we don't know. That is where this probability again comes into picture. Engineers and scientists who developed this technology, they said that there is 70% chances, based on their experience, based on the assumption, that this particular process will have high efficiency, and hence 30% chance that this may also have low efficiency. Similarly, for B, because efficiency is technology dependent, high efficiency again remains 70 for B and 30 for low efficiency. If our baseline cost is 0 and if we design a smaller unit and efficiency is actually low, we may incur additional losses of minus 100. This minus 100 is again a baseline cost, could be 100,000, could be 100 million. The scale doesn't matter here. On the other hand, if efficiency is actually low and we make a larger treatment plant, our losses are just going to be minus 20. However, if efficiency is high and we make a larger unit, we have over invested, and in comparison to the zero baseline, we are going to spend additional $50 or 50 units of money. Now, with this information, we have to essentially take the decision. And this is where again we can easily calculate expected cost of A as 0.7 times 0 minus 0.3 into 100. For B, this particular cost would be given as 0.7 into minus 50 plus 0.3 into minus 20. We get these answers as minus 30 and minus 41, which tells us that despite the uncertainty in the efficiency, if we go with A, we are going to incur the cost of minus 30. Despite the same uncertainty, in a larger plant, we are going to incur minus 41. Now, I have a rationale to make a decision despite the prevailing uncertainty that why A should be preferred over B with the given information I have. And that is what probability does in the decision making. I hope by now we are convinced that designing a problem, talking about a real world thing is sometimes much easier. And when math comes into picture, lot of pieces have to be put together. And our objective in our next discussion would be to equip ourselves with these fundamentals so that all these concepts that look very intimidating, full of maths, equations now becomes much easier, in fact, much more trivial when we have to apply to real world examples. So these two real world examples actually show us that probability is integral part of decision making. It objectively helps us choose among available options. However, before we go into detail, some mathematical foundations is needed and to find answer to these particular problems. So let's get started with the fundamentals of probability. If some of you are familiar with concepts of probability, you may watch this particular portion quickly. However, I still recommend that you pay attention to the finer details because the more you read, understand, learn about probability, the more we find that there are many hidden details to this fascinating world of probability and statistics. So when we talk about probability, all of you might have learned in your high school or senior secondary school mathematics that probability is numerical measure of likelihood. Sometimes this definition is also called as naive definition of probability because it just essentially talks about probability in a very simple word, that is total number of occurrences or favorable occurrences to be specific divided by total number of outcomes of a particular event. One very simple example, coin toss, two possible outcomes. If you have called for head, probability of head is 1/2 because in that case, head is the favorable outcome. Same applies to the dice, 1/6 and so on. So that naive definition of probability indeed helps naively quantify what is the what is the probability associated with a particular outcome, which in this case is a favorable outcome. When we talk about floods, of course, floods are not favorable. So droughts are not favorable to us. But here in probabilistic sense, it's an event for which we are interested to quantify the probability. So favorable doesn't necessarily mean what we want. It means that that what is a particular event under interest. Now, if we have to estimate probabilities, how we are going to start, because if you saw previous example, we said 70% chance it is going to be a high efficiency plant, 30% chance low efficiency plant. Or when we were talking about floods, we said that it has been observed that flood happens 1.5 times in a particular year. How did we arrive at these particular numbers? So whenever we estimate probabilities, we may have certain time series where there are certain number of observations, and then we simply count what we also call as the frequency count, how many times that particular event of interest has happened. Again, going back to coin toss, if we toss coin 10 number of times, we notice that 5 times we got head, we will simply say that probability of getting a head in this coin toss is 5 by 10. Also, it may happen we may have 6 or 7 tosses in which head showed up coincidentally, if assuming that the coin is fair. That is, that the result is based on empirical observation. That is, you tossed a coin 10 times, out of which 7 times it showed up the head. You said that, probability of getting head on this coin is 7 by 10. Nobody can deny, because you did experiments, even if coin is fair, because your estimate of probability is based on an empirical evidence or the experiment that you did. There may be certain prior condition associated with a particular setup that can also help us estimate probability. Going back to the coin toss, if you are 100% sure that this coin is fair, indeed fair, doesn't matter how many times it shows up head, you will still say that probability of getting head in next chance is 1 by 2, because this estimate is based on prior assumption or prior condition, where you are conditioned to think that if it's a toss coming out of a pocket or a wallet, it has to be a fair coin, it has not been tempered. So probability of head remains 1 by 2 irrespective of previous outcome. So it may be based on certain prior assumption, prior experience with a particular system or event under consideration. For example, in wastewater treatment plant example, when we were saying 70% of being high efficiency, 30% being of low efficiency, that estimate of probability would exactly fall onto this based on certain prior conditions that we have ascertained this particular number. And third way is subjective judgments in combination with evidences, what we call as priors, evidences, and posteriors. And these three words are often combined together in Bayesian frameworks. You might have heard of Bayes' theorem. Bayes' theorem exactly does that it combines certain subjective judgments, what we often call as priori, with the evidence to come up with an updated probability or updated posterior of event under consideration. So based on these three numbers, three methods or three ways to estimate probabilities, we often end up with probabilities of things going right, things going wrong. Interestingly, in this course, our focus would be to work on with the estimates of probabilities that would be given to us or that would be deduced from empirical evidences. We will not over worry, okay, what is the exact theorem or rational governing derivation of this particular number, because our focus is on science of decision making, risk reliability. So we would take value of probabilities as and when they are provided, and if we have data, we will find ways to estimate these particular probabilities. Now, whenever we talk about probabilities, there are few concepts or few definitions that we have to be familiar with. One we call as sample space and sample point. So to illustrate what a sample space would be, let us consider a box, what we call as S. Anything that is a possibility in our probability space has to be within this particular S, and we call that this box or the space inside this box is a sample space. For example, when we talk about coin toss, we may have two Venn diagrams, one representing heads, one representing tail. So everything about a coin toss is contained in this box, and we are assuming that coin falling on its edge is close to zero. Again, we cannot rule it out, but again, in practical scenario, we can only say heads and tails are two possible outcomes. Everything is included here. These two events are also sample points because head is one possible outcome, tail is one possible outcome, and these are two individual possibilities within a sample space that we sometimes call as sample point. Now, this sample point can be discrete. For example, in coin toss, it's head or tail, or it can be continuous. If I'm talking about flood level in the river, flood level of 5.5 feet, flood level of 5.52 feet, or flood level of 5.6 feet, all these three values are can be plotted on a number line or on a continuous number line. Hence they can also take the continuous value. So these sample points can be discrete or continuous. In probability, collection of multiple sample points is sometimes called as an event. I can say that river is considered to be in flood state if its water level or depth of water is greater than 7 feet. Now the flood event now constitutes all the levels which exceed 7 feet, 7, 7.1, 7.2, 7.3, and so on. Hence, these all were individual points, but now I have collected them together to call them as an event when depth is greater than 7 feet. So again, as I gave you an example, discrete sample points in case of floods would be number of floods in a given year, and continuous sample points would be depth of water in river during each flood level. Let us further bolster our concept of sample space, points, and events with help of this river example. That is, consider that historical data of flood. That means we have made some observation and we are essentially going to deal with aleatoric kind of uncertainty here. Suppose that annual maximum flood level above mean river flow ranges from 1 meter to 5 meter. If annual maximum flow is measured in an increment of 0.1 meter, then the sample space of flow would be 1, 1.1, 1.2, all the way till 5. And when we say that the event of annual flow exceeding 3 meter is considered a flood, we would reduce our event of interest to 20 sample points. So sample points can be many and event can be subset of these particular sample points depending upon the thresholds that we have chosen for a particular event to be considered as an individual cluster of similar kind of possibilities getting realized. Now, if we talk about some special events, we can have an impossible event. Impossible event is typically represented by phi or an empty set. One example could be getting a number 7 on a roll of a dice. It's an impossible event. Hence, it's a phi. It's an empty set. There is something called a certain event. When we talk about coin toss, either getting head or tail is a certain event. And if you notice, this certain event also coincide with our definition of sample space, because everything summed together in a sample space is a certain event, because nothing can happen outside sample space. If we talk about flood levels, getting a flood between 0 to infinity, it's a certain event. Sometimes we are not excited about certain events, because if I tell you that, there is a river and it can flood with probability anything between 0 to 1, there is no value of this particular information. but it is important to specify that 0 to infinity is my sample space, and I would be interested into further specifications of this sample space that may be of interest for me for decision making. Then there is something called as complementary events, that is outside E. For example, if my event E is having head on a coin toss, E complement would be having a tail. If E is flood, E complement would be not having a flood. Not necessarily drought, but at least flood is not there if it is not the drought. So anything that is not contained in E becomes the E complement. And this is the notation that we encounter often when we talk about events. Now, these events may further have certain unions or intersections. So, in case of coin toss, there was no intersection of these particular events, so we can draw two different Venn diagrams. However, these two events can also have intersection in a different context. So let us say that this is event A, this is event B, and when both of them are occurring simultaneously, we say that it's an intersection. Example could be that A represents high rainfall and B represents flood in river in same location or same region. Now, high rainfall may or may not always translate into high flood levels in the river, but sometimes it may happen that high rainfall can cause flooding in the river, or it coincidentally may happen that because of some reservoir operations in upstream, there is enough water in the river and high rainfall happened. So there is a possibility of intersection that we may have high rainfall as well as flood in the river at same time, both by chance or by causation. Or it may also happen that high rainfall does not necessarily translate to flood, or there is high water level in the river but there is no rainfall in that particular region. So we may say that all three regions are possible where A and B are happening exclusively or they are happening in the intersection. When we talk about intersection, as the name suggests, we are talking about the region that I just highlight now. And when we are talking about union, we are talking about all the possibilities that either A happens or B happens. Either A or B is typically union. And whenever we talk about A intersection, we are essentially talking about this, and that this happens as well as that another event B happens. This emphasis in or on and would becomes very, very significant as we continue our discussions on various events. Hence, whenever I am going to use phrase like A or B, I am essentially talking about the unions. When I am talking about A and B in probability sense, I am essentially talking about the intersection. So this emphasis has to be kept in mind as we build our discussions on the concept of probabilities. I already discussed this particular example, that about rainfall in region X and overflow in same region or another region, and we can essentially talk about the intersections and unions in context of any event under consideration. Now, another kind of event that we are interested in is that mutually exclusive events. As I already mentioned, that there is no intersection. When we talk about intersection in coin toss, either it's heads or it's tails, so there is no intersection. In case of floods, we may say that let event A be flood caused by heavy rainfall and B be no flood in that particular region. Now, either you have flood or you don't have flood. So this is a classic example when there is no intersection possible between these two particular events. So whenever we have to draw it in the Venn diagram space, we will say that this would be event A, where there is flood, and event B is everything outside A but does not intersect with A. And we say that these two events, as they as their terminology suggests, cannot occur simultaneously, and hence these are mutually exclusive events. Sometimes people confuse mutually exclusive and independent events. So let us try to understand what is this independent event. So again, let us talk about two cities, X and Y. X and Y are 5,000 miles away from each other, or 5,000 kilometers away from each other, whatever unit you are comfortable with. There is heavy rainfall in region X, and this happened with some probability of this heavy rainfall equal to 0.5. And there is a traffic jam in region Y. In on a given day, this may happen with an event of 0.3, let us say. Now, both of these are the events happening on the same day at a same time, but traffic jam is not at in region Y is not caused by heavy rainfall in X, because they are far away from each other, and removing any possibilities of teleconnections, these two particular events are independent, although they are happening at the same time. One event is not being influenced by the other, or traffic jam is not conditioned on the heavy rainfall, and heavy rainfall is not conditioned on the traffic jam. So these two events are happening independently of each other. Another example is that I am tossing a coin. I got heads in this particular trial. If it's a fair coin, uh, in first outcome I got the heads. In second outcome, I can either get heads or tails, because the next outcomes is independent of the previous outcome if my coin uh, is not biased. Now in this case, in coin toss example, these two events, they also happen to be mutually exclusive. Why? Because either head will happen or tail will happen, and they also happen to be independent. On the other side, when we're talking about heavy rainfall and jams in two different cities, these two particular events may not be mutually exclusive. There may be some overlap in between both of them, but they are independent. Whenever our events are independent and we know their individual probabilities, we can simply multiply them and get our answer, that what is the probability that both of these things will happen. So for example, if probability of extreme rainfall in city A is 0.5 on a given day, and probability of traffic jam is 0.3 in another city, if somebody asks me what is the probability that there will be heavy rainfall in region X and traffic jam in region Y, I will simply say that if both of these things have to happen together, probability is 0.15, because I can simply multiply, as they are not conditioned on each other. Now, this concept of independence would be used many times to simplify our lives whenever we are dealing with data points from real world, when we exactly don't know which event is conditioned on what, or determining this conditionality is difficult. And hence I would re-emphasize to understand difference between exclusiveness and independence bit carefully. So I've been using this word conditional, right? Probability of rainfall, not conditioned, not caused. So let us begin our introduction to this word conditional probability. It essentially says that probability of event A, given that event B has already occurred. And we often represent it as probability of A given B. And mathematically, probability of A given B is equal to the intersection of A and B divided by probability of B. Now, if you see here, what this is doing, we know that probability of any event is less than equal to 1. Whenever we divide any number by a number less than equal to 1, we are increasing or inflating its magnitude. And that is what conditional probabilities do to us. When we have probability of A equal to certain value, let us say 0.3, and we say that it is conditioned on some another event B, and we already know that B has happened with certain value. That means now we can have affirmation or a probability estimate about A with much higher confidence. And that's where this conditional probability comes into picture. That is, without that information, I have certain estimate of that particular event happening. Now it was conditioned on another event which has already happened with certain probability. So it results me in a lower uncertainty or increasing my confidence of probability of A happening given that B has already happened. That is why this concept of conditional probability is very important in engineering, because it essentially helps us add evidence to the prior belief that we have about a particular system. Because if you are dealing with a probability in range of 0 to 1, you are having full spectrum of uncertainty to deal with. If I can find a way to reduce that 0 to 1 from, let us say, 0.3 to 0.8 or 0.4 to 0.8, the range of that uncertainty has now reduced. And that is what we essentially need in engineering systems. That is, rather than dealing with full spectrum of uncertainty, can we go behind the conditional events and reduce the uncertainty associated with the phenomena of interest. Again, to give example in context of flood, let us say my event A is that flood occurs in region X, and B is there is a heavy rainfall in region X. When I talk about probability of A intersection B, I know the value as 0.3 based on certain data estimates that I have. Probability of heavy rainfall is given to be 0.5. Then I can estimate probability of A given B has happened as 0.3 divided by 0.5, and this would come out to be 0.6, as simple as that. Now, interestingly, if I have conditional probability known to me and probabilities of intersection known to me, I can also work out on the probability of that particular event on which the other event was conditioned. So in this case, all I need to know is probability of B. If it is conditioned on B, probability of B can be easily determined as probability of A intersection B divided by probability of A and B. I can also write this as probability of A intersection, or I can write probability of A intersection B as probability of B intersection A into probability of A, which is equivalent to probability of A given B has happened into probability of B. And now these two highlighted terms are equal. And when I simplify that, I am essentially looking at the Bayes theorem or one of the Bayes formulation. So this conditional probabilities are often encountered whenever we have some prior information about the events that are associated with us. Now, when we talk about statistical independence, we already learned that probability of A and B is simply probability of A times probability of B. With this concept of conditional probabilities introduced, we can further dive into this concept of statistical independence and say that probability of A given B simply becomes probability of A, because now A is not conditional on B because these two events are independent. Hence, probability of B given A can also be written as probability of B, because does not matter if we know anything about A when we are determining probability of B, because these two events are independent, and that is also captured in this notation of conditional dependence. So now coming to the last concept of this introduction to basic terminologies around probability is the concept of total probability. Mathematically speaking, if B1, B2 or Bn are mutually exclusive events and exhaustive events mean that when their probabilities are summed together, they should yield the value of 1. And mutually exclusive is that either B1 will happen or B2 will happen or B3 will happen and so on. Then for any event A, we can write probability of that particular event happening using the summation of probability of A given B1 into B1 plus probability of A given B2 into probability of B2 and so on. And this will give me the total probability of A being happening, which originally was conditioned on multiple mutually exclusive and exhaustive events. To reinforce this concept, let us look into a very simple example, which is essentially on, again, flooding. That is, that the flooding on the river in a spring season will depend on accumulation of snow in the mountains during winter season. Now this accumulation of snow, it could be heavy, represented by H, it could be normal, represented by N, or it could be light, represented by L. Now either it is heavy or normal or low. That means these are mutually exclusive because these two cannot happen simultaneously unless we are talking about some fuzzy sets, but these are not fuzzy sets here. These are also exhaustive because snowfall is either high or normal or low or non-existent. If we say that non-existent is also clubbed with L. So this essentially satisfies the conditions of being conditioned on, because it has to be mutually exclusive and exhaustive. Our question is that can we determine what would be the flooding in the event if this entire information is available to us, given that there was a heavy snow in the previous season, probability of flood is 0.9. Given that there was a normal snow, probability of flood is 0.4. Given that there was a low snow to no snow, probability of flood is 0.1. And it makes sense also to see these particular values decreasing as the amount of snowfall is reducing. Also, it is given to us that probability of extreme snow or high snow is 0.2, 20% chance. Probability of normal snow is 50% and probability of low snow is 30%. And we have been asked that what is going to be the probability of flood. Now, when we talk about this probability of flood, this is the total probability of flood. And it is conditioned on probability of flood given that there was high snow event multiplied by probability of high snow plus probability that there would be flood given that there was a normal snow event multiplied by probability of normal snow plus probability of flood given there is a low snow multiplied by P of L. Now, if you see that when these things are happening in multiplication, they are acting as the modulating effect. That means even if probability of flood given high snow is very, very high and probability of high snow itself is low, probability of flood gets modulated or controlled. As a result of which, when we sum these together, it is essentially more like the weighted sum, where all events are not being looked upon with the same scare when we talk about floods, because chances of extreme event being happening is very, very low. However, when they happen, the amount of damages they will bring is very, very high. Hence, when we say that an extreme cyclone may cause $100 billion of damage, that doesn't necessarily mean that we are going to lose $100 billion. It essentially means that if that event happens, which itself happen with a very low probability, the expected loss is going to be much lesser value than what we expected. And that is why this discussion or quantification of risk becomes important in decision making, because the numbers of losses appear very big, but when modulated or multiplied by probability, we essentially get to know what is the exact gravity of that particular situation when that low probability events are being realized. So in this example, this simply becomes 0.9 multiplied by 0.2 plus 0.4 multiplied by 0.5 plus 0.1 multiplied by 0.3. All these numbers coming from the values here of H and L and individual probabilities as well as conditional probabilities. And when we sum, we see that the probability of flood while accounting for all snow conditions come out to be approximately 41% in a given basin. So now with these very simple concepts of exclusive, exhaustive, conditional and total probabilities, we are all set to go to next level of problems, that is around the uh, uh, dealing with these variables in much more mathematically robust sense, and we will introduce ourselves to the concept of probability mass functions and probability distribution functions in the next lecture. Thank you.